Good morning and welcome to the second program in our NASA Goddard lecture series. We have 6 more, so plenty for you to return and learn. I'm Stephanie Marcus from the Science, Technology, and Business Division. Today, we're going to talk about TESS, which is the Transiting Exoplanet Survey Satellite. It's much easier to say TESS. And TESS is searching for Earth-like planets beyond our solar system. And we're lucky today to have the deputy project scientist on the TESS mission, who led the team quite some time ago in her career that confirmed the first Earth-like planet in a habitable zone, right? The Goldilocks zone, as it's known. Dr. Quintana's path to NASA was a little bit different from some of our speakers. She grew up in New Mexico, and her father was a Chicano poet. Hopefully still is. He's still around. Yeah. So that's pretty cool. But she had no science role models. And she just happened to take physics at the University of California, San Diego, and she just happened to have as her advisor astronaut Sally Ride. So after that, her career took off, and the sky was not the limit for Dr. Quintana. So please help me welcome her to the Library of Congress.
Excellent. Thank you for having me. Can everyone hear me? I don't know how close I have to speak. Is this fine?
That's good.
Okay. So as Stephanie mentioned, there have been speakers in the past talking about TESS back when it was an upcoming mission. And so I'm here to talk about what we've learned from all of these exoplanet missions and what we expect to learn from some of the upcoming ones. And so it's kind of what have we learned since, some of those last lectures. So I want to first visit solar system formation and talk about what we know about forming our own solar system from what we can observe today, and think about what that can teach us about the origins of our solar system. How can we look at all of the clues that we see today and kind of piece together what we think happened to form all of the planets that we know of? Then I want to talk about exoplanets, some of the past missions that have produced these new planets. So exoplanets are planets orbiting distant stars other than our sun. And so we have a lot of new clues from those. And then I want to talk about some of the upcoming exciting missions that NASA has. And so all of this is kind of trying to put planet formation, piece it together, and where we think we might be able to go in the next decade. So we know of our solar system today. We have 4 rocky inner planets, and the architecture that we're familiar with are these rocky inner planets with giant planets exterior to the sun. This doesn't show everything. The solar system has lots of other asteroids and small bodies and a lot of observational evidence that give us a lot of clues to try to piece together how our solar system formed. And so just to take a step back and try to understand how we can look at what we have today and understand how this whole process formed. How did our planets form? How did everything form? And so one of the most popular theories is the solar nebular theory, and it dates back several centuries. And the idea is that our sun and all of the planets and moons and everything in our solar system basically formed from a giant cloud of molecular gas and dust that was rotating. And we see observations of this that are plentiful. Hubble has observed lots of these rich environments. And so we believe that everything essentially formed from a system like this, like a giant molecular cloud rotating really fast. And when so much mass has succumbed to its gravity, it eventually collapses. And so this is how we think stars form. We can't really understand how planets form unless we understand how stars form. And so the idea is that there was this huge cloud that collapsed under its own gravity. A lot of the material pulled in to form the early sun. And what was left was this disk of material of gas and dust. And so we think that most of our planets formed from this sort of residual gas of disk of gas and dust that formed around the newly formed sun. And so we have this basic picture that people have been building up for several centuries. And it dates back to Laplace and Kant from the 1700s, that we think our planets formed from this disk. And if you look at what we see today, there are some pieces of observational evidence that supports this whole grand theory. And a few of them are listed below. If you look at all of the planets, they're all orbiting in nearly circular coplanar orbits, meaning they're kind of in the same flattened system. All of the planets are orbiting in the same direction, as is the sun. Most of the planets and moons are also rotating around their spin axes in this direction. And so we can take together all of these observations of the motion of everything in our celestial environment and look at a lot of geochemical evidence, and everything supports this grand theory of how planets formed from this disk. And we see a lot of evidence that this has also happened beyond our solar system. And so these are a lot of real images of disks that have been observed, and these could very well be the signposts of planet formation happening around other stars. This is a wonderful video. This shows one of the first movies that people have made of actually seeing exoplanets in motion around a star. So this is actually a young star about 130 light years away. This is a direct imaging technique. And so because stars are much brighter than their planets, what you do is you block out the central light of the star, and then you can see what's happening around it. So this turns out to be a young star with a disk where we can actually see giant planets kind of like Jupiter moving around. And so we see a lot of evidence for disks and planets moving around. And this kind of supports these ideas that we have for planet formation. So once we get to this place where we have a newly formed sun and a disk of material of gas and dust, how do we think the planets actually formed from this disk? And so this is idea, as I mentioned, that dates back for hundreds of years. And so if you think about it, today we're in 2019. Basically, up until about 30 years ago, we only had evidence for our solar system. And so we have built up this idea of how the planets formed from this disk through lots of evidence from numerical models, computer simulations, dynamical simulations, and every single piece of the puzzle that you can imagine scientists from all disciplines have been putting together to try to understand how our planets formed. And so the idea is that planets formed in several distinct stages. And this early stage, from the material around the disk, eventually it cooled down until you got some solid kind of grains forming. And as everything's rotating, these grains coalesced and stuck together to form what we call planetesimals. And these are sort of the building blocks of planet formation. And so this is kind of the early stage of planet formation. This middle stage of planet formation, when you have these building blocks of material, what happens is you have rocky bodies swarming in this disk, and you get kind of the snowball effect. So this sort of shows a cartoon illustration of if you have planets orbiting sort of in their region, the bigger a planet grows, the more it's going to eat up material in its region. And so you get this effect where it's called runaway accretion, where the bigger bodies grow faster. And ultimately you get these bodies that kind of eat up everything in their orbit. And you end up with what we call planetary embryos. So these moon to Mars sized embryos that have basically accreted a lot of the material in the disk. And then the late stage of planet formation basically involves this sort of violent interaction of gravity and collisions, where ultimately everything else in the disk accretes and grows, and you end up with planets on their final orbits. And so this is sort of the classical theory of planet formation that has been the most widely accepted for our solar system. Oops, skipped on. So how old is the solar system? This is probably the nerdiest thing I've ever tweeted. This is from 2015. If you go to the Natural History Museum in DC, they have one of the oldest rocks, and this is how we date how our solar system formed. And so some of the oldest rocks on Earth, you can date back to 4.67 billion years ago. So that's a really long time ago. And that's basically where we think this whole idea of where the sun formed happened. And if you look at a timeline of just the early solar system evolution, this timeline starts at 4.5 billion years ago. And I just wanted to point a few things out because it's going to come up later that I'm going to talk about. If the birth of the sun was 4.5 billion years ago, we think that these moon to Mars sized embryos formed within the first few million years. And we also have evidence for believing that all of the gas in the disk dispersed within 10 million years after the sun formed. And so this means that you have gas and solid materials. This is a really important constraint, because if the gas is only around for 10 million years, that means that our giant planets like Jupiter, like these planets that have thick gaseous envelopes, have to have been fully formed during this time. And so what we believe is that the giant planets like Jupiter and Saturn and Neptune actually formed within 10 million years of the birth of the sun. And they were already fully formed when the Earth started to grow and actually evolve to its own size. And if you think about the difference in masses of these planets, this means that when Earth was growing, it had this dominant presence of this gigantic planet perturbing the material. And there's a lot of questions about whether Jupiter was like a friend or foe. Some people think that Jupiter was a friend because it cleared out so much material because it was so dominant, allowing Earth to form and protecting it from lots of late collisions that could have been harmful for things like life on Earth. And so I wanted to show this just because I'm going to talk about giant planets later. So going back to our solar system, again, we have sort of these two different classes. So up until recently, we know that we have a system of terrestrial rocky planets close in to the sun. So these are planets that have solid surfaces. We know Earth is in the right zone to be able to harbor life. And we have lots of big, massive gaseous planets that were around during Earth's formation, exterior to that. And so we've known this architecture for a long time. And during the era of trying to search for other planets, what we were looking for was planets around other sun-like stars. And we've been always trying to understand whether other Earth-sized planets existed, whether our solar system is typical, and all these other questions. And so about 27 years ago was the first discovery of the first planet orbiting around a star other than our sun. And this was a complete crazy surprise because these were small Earth-sized planets that were actually found around not a sun-like star, but a pair of rapidly rotating tiny neutron stars. And so these are planets that can never have life. It's a super hostile environment. But it was the first time people thought, wow, you can actually have planets outside of our solar system. And so this was not that long ago, and it was really revolutionary. And so in 1995, we had the first discovery of a planet around a sun-like star. And so this was 51 Peg. This was also a huge surprise because this is a planet that is about half the mass of Jupiter. and it was orbiting in a 4-day orbit. And so to compare, Mercury is an 88-day orbit, Earth's in a 365-day orbit. And so this is so unlike anything we ever expected, and basically threw this whole wrench into these theories that people have been refining for hundreds and hundreds of years. And so this really sparked a revolution because this showed that planets existed around other sun-like stars, and really provoked people to build more instruments and new space missions to kind of go after and see if we can find more of these. So the discovery of exoplanets really skyrocketed with the Kepler mission. Kepler was a truly revolutionary mission. It was launched in 2009, and this was built purely to answer some really fundamental questions, and those were, are there other Earth-sized planets out there, and how prevalent are they? And so we knew that at this time we had found maybe a few dozen of what we call these hot Jupiters, so these big Jupiters really close to their stars. But we really wanted to understand, are the Earth-sized planets kind of like ours? And maybe that might, put together some questions like, are there other planets? Is there other life out there? And when Kepler was launched, we didn't really know the answer. And so even the person that built the mission, when it launched, had some quotes saying that it could be that we don't find any Earth-sized planets, and that would be really just as profound as finding any, because it might mean that Earths are rare. What we found instead, first I'll tell you how Kepler looked for planets. Because planets are hard to find, one of the most successful methods is this transit method. Searching for planets with this transit method involves you looking at lots and lots of stars and hoping you see some stars that cross in the line of sight where it blocks some of the light from the star. So here you can see a little cartoon of a planet going in front of its star. At the top, you can see we measure the brightness of a star, and when a planet crosses it, it produces this dip. And so if we monitor hundreds and hundreds of these stars, then maybe we can hopefully find some planets that actually have the right orientation where we can see these dips. And so this was the technique that Kepler used. It looked at over 200,000 stars to look for planets. And this had been used before on the ground to find some of the bigger planets, but to find something as small as Earth, you really had to go into space, and that's why Kepler was built. And so this is a nice cartoon that my postdoc from NASA Goddard made, Ethan Cruzy. This shows all of the mini solar systems that Kepler found within the first 4 years of taking data. And so this is really interesting because, like I said, we thought we could maybe find no planets, or instead we found lots of planets. And so this is a really dizzying kind of animation. But what you see are all the, so Kepler found over 2,300 exoplanets and another few thousand other planets that are still waiting to be confirmed. Over 700 of these had more than one planet. So here we're just showing the kind of solar system, so stars that had more than one planet. And so all of these, the planets are not to scale, but you can see them to scale with the solar system. All of these basically mean that if you observe more than one planet in a system, they have to be really flat and aligned for you to see them transit. And so this also supports this idea that planets formed in disks. And so this was a real pleasant surprise. It's great for people that want to study planets that we found that planets are so abundant. And it turns out that planets form around all types of stars. Planets form around multiple star systems. And we found planets from as small as Mercury to much, much larger than Jupiter. And Kepler basically taught us that planets are super diverse. And then if you do statistics, Kepler looked at a small patch of the sky, but if you extrapolate, Kepler basically taught us that we think there are actually more planets than stars. And so they're truly, truly abundant. And this was a huge result that was unexpected going into the mission. So if you were to look at all of the planets that Kepler found and drop them into size bins, here's a histogram. So you can see we found Mars planets and Earth planets. On the bottom, you can see our solar system planets. And some of the real surprises from Kepler were there was a few surprises. One, in our solar system, we have Earth, and then we have the next size up is Neptune, which is 4 times the size of Earth. The most common type of planet that Kepler found was actually planets in between Earth and Neptune. So these are planets that we don't have in our solar system. And so these were not predicted. If you look on the Jupiter bin, we had predicted many, many hundreds over maybe 1,000 Jupiter-sized planets because these are the easiest to find. And it turns out that they're actually not that common. And so that was weird. That was weird. And there were a lot of other weird oddities. And all of these are huge clues to our planet formation theories because what we pieced together for many centuries, basically, does that mean that our solar system is unique and formed in its individual way? Or does it mean we need to expand our thinking and understand, is there a unified way that planets formed? Or maybe planets form in all different ways. And so Kepler really brought us so much information that kind of will entertain planet formation theorists for a really long time. So one topic I've been really interested in studying is forming Earths and trying to look at the question of what is the typical environment where Earths might form. And so we have Earth in our solar system. That's great. But if you look at all of the observational evidence, there are a couple things I'm going to focus on. There's also many more that I don't have time to. But one of them that I mentioned before is that Jupiter analogs near Jupiter orbits at 5.2 AU. AU is the distance in astronomical units from the sun. Earth's at 1, Jupiter's at 5.2. These long period Jupiters are actually quite rare. And so one thing I wanted to work on is doing computer models to try to understand, well, if you're trying to form Earths, what happens if you don't have this gigantic, giant planet perturbing the system? What does that do to forming your Earth? What does it do to it having water? And answering all these types of questions. The second regime I've been really interested in is looking at small stars. And so Kepler was really focused on sun-like stars because we were trying to find other Earths. And we were trying to understand are Earths prevalent? It turns out that planets like Earth form around all types of stars. And actually the smallest stars, these stars called M-dwarfs, typically have more planets than sun-like stars. And so these M-dwarfs are planets that are 10 to 50% the size of the sun. We didn't know if they were common exoplanet hosts, and it turns out they are. And so another topic I've been studying is how does planet formation differ if you're forming around these tiny small stars? And can you form Earths just like you can around sun-like stars? So I'll talk about those just for a little bit. So for the first one, for Jupiter, if you take all of the observational evidence, not just from Kepler, but just take everything, there's ground-based surveys that have observed stars for many decades. All of them point to the sign that these Jupiter analogs, like what we have in our solar system, is rare. We think less than 10% of stars have these giant planets. So the typical environment for an Earth around a sun-like star could be a system without a giant planet. And so I'm not going to go into the detail of my computer models, but I just wanted to show you this animation. It's a little dark, sorry about that. But I have, we did some numerical simulations where we start out with hundreds and hundreds of rocky bodies and planetary embryos in a disk, and we evolve it forward in time just using Kepler dynamics, and planets can grow and evolve as we think they do. On the left is a disk around a sun-like star. The green just shows each body is represented by a ring. So the green just shows the distribution of embryos. The disks are exactly the same on the left and the right, but on the left we include Jupiter in purple and Saturn in yellow. And so I'm going to start this movie, and then you can see how these planets evolve under the presence of this giant planet with and without giant planets. So, well, it's hard to see from here. I hope you can see a little bit. But essentially, what we think happens is that these terrestrial planets form within 1 to 200 million years. On the left, Jupiter and Saturn have this clearing effect that I mentioned. And so you end up with these interterrestrial planets. On the right, if you don't have Jupiter and Saturn to clear out any material, you end up with systems just like those in our solar system, but you end up with even more planets and a swarm of a lot of material that just sticks around. Because if you don't have anything giant external that's taking out a lot of that material, that's just going to hang around for a really long time. And so what does that mean for forming Earths, and what does it mean for habitability of planets? And so on in each plot, I've shown just a handful of the results of our simulations. On the top are our solar system planets in green. So there's Mercury, Venus, Earth, and Mars on the top, and then Jupiter is a huge one. So on the left, you can see the types of planets we find when we include Jupiter and Saturn. And so within 2AU, if you do enough of these, they broadly resemble the ones in our solar system. On the right, we don't include giant planets. And so you can see within about 2AU again, we form Earth analogs in our simulations. But again, we have many, many other planets just kind of sticking around. And so if we think that giant planets are rare, it could be that we have lots and lots of systems like this with many, many terrestrial planets around sun-like stars out there. And so this is interesting. This is the same simulation without giant planets, fast forwarded to 2 billion years. And so you can see that all of the material still hangs around for billions and billions of years. And so if you remember, our solar system is 4.5 billion years old. We can simulate these kinds of systems for billions of years, and hardly any material is ever tossed out. Like less than 1% of the material is ever tossed out in these simulations. And so these are nice ways that we can use computer models to try to understand what might be happening in these planet formation environments that are what we used to call extreme, but maybe it's not extreme. So it could be that our typical Earth planet that forms around a sun-like star could be in this types of environment that's surrounded by a lot of material for billions and billions of years. And you've probably heard that there's huge efforts by the planetary defense looking for near Earth objects, and that's a huge sort of risk to our life here on Earth. We want to track everything. If you consider planets in this, then you can imagine that there could be material hanging out for a really, really, really long time that can increase your chances of getting hit later on. And so these are the types of questions that we want to ask, is if what's a typical environment for an Earth-like planet? How vulnerable is it if it were to obtain life and oceans and atmospheres and all that? What are the chances it might get hit by a huge asteroid later on in life? And so these are things we can actually measure with these dynamical models, which is pretty interesting. So moving on to the next case, looking at planets orbiting these small, tiny stars. And so M dwarfs are really interesting for a lot of reasons. One of the main reasons is that they comprise over 75% of the stars in our galaxy. And when Kepler was launched, it was really looking at sun-like stars because it really wanted to find Earths. And so, we always look for what we know. We look for Earths around sun-like stars. It maybe observed a couple, 1,000 M dwarfs, but that wasn't really the focus. If you were to look in our solar neighborhood and draw a huge circle within 80 light years of us, then you can see this cartoon that shows most of the planets are M dwarfs. You don't see them because they're small and dim, but if it turns out, from what Kepler told us, that these are the most common types of planet hosts, they typically have more than one planet. We found lots of Earth-sized planets around these types of stars. And so if we really want to answer these big questions, like how prevalent are Earth-sized planets and even how prevalent is life in our universe, then we really need to understand how planets can form and whether Earths can form and also habitable Earths. And so these are really great targets to focus on now that from everything that we've learned from Kepler. And so here's a little cartoon showing a sun-like star next to one M dwarf. This is an M dwarf on the bigger size. It's half a solar mass star. So planets orbiting M dwarfs are easier to find with the techniques that we've been using. If you were to place a planet around each of these stars and look for this transit method, what the transit method measures is a brightness over time, and it measures the amount of decrease in light when a planet blocks it. So if you have the same size same size planet, if it's orbiting a smaller star, it'll block a much bigger piece of light. And so there's a few reasons. This is just one technique I'm showing, but there's lots of reasons why finding these planets orbiting these tiny stars is much easier. And so besides the fact that they're abundant, they're easier to find. There'll also be the next targets that we're going to be searching for with the upcoming James Webb Space Telescope. We're going to be really looking at planets orbiting these small M dwarfs. And so this is really this huge new research area that didn't exist pre-Kepler. And this is like really what a lot of people are focused on is, can planets form and how can they be habitable around these types of stars? And as Stephanie mentioned, this is one system that we worked on, Kepler 186f. So this was detected with the Kepler Space Telescope. It was a team that I helped lead to confirm it was the first Earth-sized planet orbiting in the habitable zone of another star outside of our solar system. And Kepler 186 is a half solar mass star. Another thing I didn't mention is that these M dwarfs are smaller and cooler. Because they're cooler, the habitable zone, which is the area where they could potentially have liquid water on the surface, is much closer in. So it's kind of like this campfire effect. Like if you want to stay warm, you have to be much closer in. So we have these, we have lots and lots of multiple planet systems around these tiny M dwarfs. But it also means it's a much different environment than what we've been studying with solar system and G-type stars. What it means is you have planets much closer in, because just if you think about Kepler's law, the closer planets orbit, the faster they go. And then if you think about the planet formation process, this means that they have much higher speed impacts. And so when everything is growing, it's a much more violent environment. And so planets forming around M dwarfs, especially if you're looking at Earth and habitable zone planets, it's very, very different from sun-like stars. And so you have to think about, can you form planets, but also if planets can form and accrete water and atmospheres, if they're going around like super fast and getting constantly bombarded, then it's a real challenge to actually be able to maintain these atmospheres and oceans for a really long time. And so this has been one of the main challenges in research when people are trying to understand whether planets can form and be habitable zone around these tiny stars. And so I'll just go over this briefly. We did some experiments doing the same type of planet formation around Kepler 186f, which is a half solar mass star again. Each of these panels just show time, a snapshot in time for a simulation. So we start out with a disk of planetary embryos and evolve them forward in time. This just shows their at the bottom. It shows their distance to the star, and essentially, if you simulate planets forming around these small stars, everything happens so much faster. So these planets actually form on orders of 10 million years instead of hundreds of millions of years. And so, again, it's a different environment and it's a different process that we have to simulate. And so we did this experiment looking at what types of disks we would need to try to form these types of systems. And it turns out that it's very different from our solar system. It turns out that you need lots and lots of material to begin with. And then if you evolve it, you eventually get these planets. And so just doing a couple simple experiments, trying to do our same types of planet formation around these low mass stars, we already know that we need to change our ideas compared to what we were doing with the sun-like stars. We have this nice picture trying to form the solar system planets in our solar system planets. Come to M dwarfs, and it turns out that things aren't quite fitting right. And so I won't get into the details, but what we learned is that you need to invoke more something else, because the way that we thought planets form doesn't really work in these types of systems. And so this is really interesting. We also measured all of the impacts that formed these Earth-sized planets and could quantify how energetic they were. And so I'm not showing much just because this is preliminary research, and I'm excited. I'm having an intern come this summer to actually work on this and probe it further. But if we really want to understand if Earth-sized planets can form around the most abundant stars, this is something we need to understand. I also wanted to bring up one of my students that just recently won first place in this Regeneron Science Talent Search, looking at the Kepler population of exoplanets. And so I showed you this cartoon earlier. So what we found, if you look at all the multiple planet systems, there are some planets that seem really closely packed in, where it doesn't look like you can fit any more planets, or the systems would be unstable. And there are some systems that have like wide gaps. And so my student is currently investigating this. Does it mean that planets just form like that? Or it could mean, because we're looking with a transit method, it could mean that there are planets in the gap that are just not aligned quite right where we see them transit. And so she's trying to quantify whether we're missing planets because they're there and we don't see them transit, or if planets just don't form efficiently like we think they do with simulations. And so this is a nice, fun project, and I'm glad she did very well investigating this. And then we're putting out a paper later to try to put some measurements on what we think. If you look at our numerical simulations, planet formation should operate quite efficiently. And so why are we missing these? And these are some really interesting questions now that we have hundreds and hundreds of multi-planet systems from Kepler. So I'm going to move on to NASA's, I want to say newest planet hunter. I guess there have been talks here before pre-launch, but TESS is a transiting exoplanet survey satellite. And TESS is the latest mission to look for planets around other stars. This is just a nice launch video to remind you that it just launched last year, and we're already getting lots and lots of new planetary systems that are providing wonderful, wonderful clues to help us in this search to try to figure out these planet formation puzzles. And TESS was one of the first astrophysics missions on a SpaceX rocket. So yeah, we heard that some people from SpaceX weren't so excited because TESS got a lot of attention and they're used to, SpaceX getting a lot of attention, but but it's wonderful. They were fantastic. They made this beautiful patch and everything. And so that was exciting. So TESS has different goals from Kepler. So as I mentioned, Kepler looked at a small patch of the sky, and it really wanted to answer whether there were other Earth-sized planets. Building on that, TESS is doing a near all-sky survey, and instead of looking far and deep, it's looking at planets that are in our solar neighborhood, like that plot I showed you with all the stars within 80 light years. It's really going to try to find planets around all of our nearest neighbors. It's going to look at lots of M dwarfs. And there are a few major goals. One is to find new planets for the upcoming James Webb Space Telescope to probe. So James Webb isn't a survey telescope. It's really going to do a deep dive on individual planets. And before we feed planets to Webb, we want to make sure that these are really good targets. And so we want to find planets that might have atmospheres that we can really understand. And so that's one of TESS's goals. The other, because it's going to find planets around nearby bright stars, it means that we can use all our resources on the ground and really follow up and with all the telescopes and try to get masses and more measurements of all the planets so we can really understand this population of Earths and super Earths and mini Neptunes and really try to understand what those are all about, because we still don't have too much information on this population that's the most abundant from what Kepler told us. We really don't know much about them. And so again, Kepler, one analogy I heard is if you were to hold your hand up to the sky, the Kepler field of view is about the size of your palm. And so it's less than 0.25% of the sky. And within that just tiny patch, it found thousands and thousands of planets, and it taught us so much. And so TESS is looking much closer to us, but doing a much more complete survey. And it has a 2-year survey. It has fuel to go on for many, many years. And so it can go well beyond the survey and do a lot of really interesting exoplanet research and also other research. So TESS just started getting data on the ground and public in December. And so right now we're just at the tip of the iceberg. So this is a first look at what the TESS orrery would look like. So this is just a handful of the multi-planet systems. But I expect the number of planets to grow nearly exponentially now that we have a whole community of scientists that have been used to working with Kepler that are adjusting their tools and looking for planets, and everything should go, well, I would expect this to almost look like the Kepler orrery. We'll see how our predictions pan out with TESS. So I'm not going into too much detail about TESS, but I wanted to mention this website, exoplanets.nasa.gov/TESS. This is sort of a page where we're updating the number of planets that TESS is finding. We have 11 confirmed planets and a few hundred candidates. So candidates means we're still looking at them. And right now we have 100 candidates that are in between the size of Earth and Neptune. And so this nice regime where, again, we can try to learn more about them. Looking ahead into the future, W1 is a NASA mission that will launch in the mid-2020s. And so W1 has a huge amount of science it's going to do dark energy. It's going to answer huge questions about our fate of the universe. But it does have an exoplanet component. If you can see the outline, that kind of looks like a space invader. This is the field of view of W1st. And if you can look, I guess in the middle or below that is a small square, and that shows its comparison to Hubble. So if you remember seeing these Hubble deep images, like you see these posters where you see all these beautiful galaxies and all this amazing data, W1st is going to have 100 times the area as Hubble, but with the same clarity and depth. And so we're going to learn so much more with these footprints of W1st. And so it has a few different exoplanet goals. It's using a technique called microlensing, which you can go to the W1st website. Like, that's way beyond the scope of this talk, but it's a technique that's complementary to the transit technique to find planets. It's expected to find thousands of planets. And the nice thing about this is it's going to find a different parameter space than what Kepler and TESS has been looking at, which I'll show you in a minute. It's also expected to find lots of transiting planets, and it has another component where it's doing this direct imaging. Like I showed you that video earlier of the orbits in motion. And so it has this really nice component where it's actually going to directly image exoplanets and do some proof of concepts, because NASA's also building more missions for the future. And we in the future is really direct imaging. Like, now that we know all about planets, we want to learn more and actually be able to image them. And so W1st has this really nice tech demo to really advance the field in this direct imaging. So completing the planet census, this is sort of a plot to show the parameter space that W1st will see. So if you look on the right, this shows sort of the orbits of our giant planets in our solar system. And then zoomed in on the left are the terrestrial planets in our solar system. And so really what Kepler and TESS have been probing are just planets in the terrestrial region. You know, Kepler was designed to find planets like Earth at 1 AU around sun-like stars. One thing that Kepler wanted to do to validate a planet was, I talked about this transit method, and wanted to see a planet transit at least 3 times just to make sure it wasn't a fluke. And so we see Earth, Earth goes around the sun every 365 days. To see Earth's around suns, you really need to observe stars for at least 3 years. And so Kepler was a 4-year mission, is really sensitive to planets within Earth's orbit, roughly. And so that's why we're finding all these tiny solar systems. And TESS's 2-year mission, we're looking at a much larger part of the sky, but we're also seeing we're not observing the stars for long enough to see planets on wide orbits. And so we're also covering this, small parameter space. What W1st is going to be huge at, and is really going to be revolutionary, is it's going to be sensitive to planets much wider. And then I told you about how Jupiters have a huge influence on planet formation. We really need to complete the census and understand, are Jupiters really rare? What's out there? Maybe Saturns are prevalent, and answer these big questions, because it turns out a lot of people have been looking for Earths and trying to understand what's a frequency of Earths, but you can't really understand that question without knowing the frequency of these Jupiters and these outer Saturns. To look at it one other way, this is a plot that also shows the parameter space. On the x-axis is the distance to the star, and then the y-axis is the planet mass. So in red, you can see sort of the region that Kepler covered. And again, you can see Earth in the middle, Earth at semi-major axis of 1 AU and a mass of 1. And so Kepler was designed purely to try to capture these Earths. And W1st is going to do this huge parameter space and really complete the census of planetary architectures. And so as a planet formation theorist at heart, this is what I'm really, really excited about for this mission. And so there's a scientist at Caltech that decided to plot what's the number of planets that have been detected by year. And so it turns out that the number has been increasing exponentially, really nicely. And it's the person that first plotted this on Twitter is named Eric Mamajek, so we called it Mamajek's Law. But if you actually project out to 5 years and 12 years with TESS and Dolby First, they follow this line. And so we have all these clues I talked about right now, but it's only going to get better. We're only going to get more systems. With TESS, we're going to get not only demographics and where planets are, but we're going to learn a lot about their masses and compositions and get a lot more rich history, which you need to plug into these planet formation models. And then again, W First is going to teach us so much about what we haven't been able to really probe. And I love this graphic. It's by an artist, David Curtis, mainly to show that NASA has this whole suite of missions that have been really focused on trying to answer these questions. But also, there's a whole swarm of ground-based telescopes I haven't talked about, and other international telescopes and surveys I haven't talked about. And so there's so many surveys out there that are also collecting a lot of really great information that are going to help us, try to solve these questions. And so brief overview of what have we learned from our missions. Kepler taught us more planets are more prevalent than stars, and that's huge. That's probably one of the, most profound results that I can think of from Kepler. But we learned a few other things, like Jupiter's are probably rare. Planets are more abundant around small stars, and planets in between the size of Neptune, which we don't have in our solar system, are very prevalent. TESS is going to observe over 85% of the sky just in its 2-year mission, and will observe more if it gets an extended mission, which I expect it to do. It's going to find hundreds of these super Earths, and it's going to find hundreds of these multiple planet systems where we can get more information about them. And we can get more information that we can understand what types of disks might have formed them. Dolby First will complete the census. It's going to be sensitive to these cold planets. It's also going to be sensitive to planets as small as the moon, and maybe even the size of Ceres, which is the largest asteroid in our solar system. And so that's going to do another whole revolution that we don't even know what answers it might bring in that time. And this is my last slide. I also wanted to mention that solving all of these puzzles and trying to put together this whole picture requires an interdisciplinary approach. And so Goddard has recently put together this really nice consortium. It's called SEEK. It's named after Pierce Sellers, who was an astronaut that was really into climate change. And the idea is to bring together scientists from all divisions, from earth science, planetary science, astrophysics, and heliophysics, to really come together, put all the knowledge that they know together to understand how exoplanets formed, because you need people to observe them, you need people to understand atmospheres, and you need people to understand the stellar environment. And this is a really nice consortium we have of hundreds of researchers. And so I'm really excited. I hope that more people from SEEK will come give future talks here, because we're really not just isolated anymore. We're trying to solve these big picture questions together. And that's all I have, so I'll take questions. No, I have a lot more.
Yeah. I'm waiting to have my own exoplanet, so no traffic. We'll have questions now, and please repeat the question so it'll be on the tape.
Sure. Do you want to pick or?
You go ahead.
Oh.
I don't want to blame.
How much coordination in this program is there with scientists in China and in Russia?
Well, I don't know about the specific countries. I mean, there's a lot of interdisciplinary input for, do you mean for the specific missions? Or,
You have two missions, TESS and W first.
so,
Some of these other countries have other missions that fit in between.
yeah, so I don't know exactly. Oh, so as far as partnerships, I don't know exactly official partnerships, but the one really nice thing about TESS and will be first is that all the data is public immediately. So regardless of who builds the mission and who puts the data out, the data is public to everybody. And we learned this from the Kepler and K2 mission. So K2 was an extended mission from Kepler. One thing we learned that is if you put the data out, you get a lot of more research papers coming out from people from small schools, people from small countries, young scientists, early career scientists. And so we have participation from pretty much everybody as far as using the data and doing some really nice science.
I still have a problem with like the clumping aspect of things heating up and somehow becoming spherical. Can you talk about maybe two-part question? One, is there some type of work being done on a planet equation, where if I put a little of this in and a little of that in, energy in this, I get something that turns into a planet, versus material that's still out there that we're finding that is potato shaped, that is obviously not considered a planet, and where you get to a moon-sized shape that turns into a planet, where if it's a little smaller, it won't be a planet. Is there any thoughts on that?
So that's a big active area of research. So the simulations I've been talking about are much more higher level than that. When we did our planet formation simulations and when we actually created the code to have bodies stick and grow, we did use a lot of, they were based on a lot of models where there were teams that did individual models where they looked at what would happen if like two bodies collided at different geometries and different masses and different shapes. We haven't gone to that resolution. I mean, at some point, even with the models that we're doing now, which are kind of crude, and actually if I take a step back, when I was in grad school, I started these planet formation models, and we would assume that anytime two bodies would collide, like two rocks would collide, they would stick. And that was the kind of norm. And even doing those simulations on the NASA Ames supercomputer would take a month. So we've implemented new collision models, especially with this low mass M-star regime, because you have to consider fragmentation and erosion and not just assume everything sticks. But even with those, we're not looking at the resolution that you're talking about, because it's just not computationally tractable. But there are people that are doing individual, collision simulations, and that is a huge area of research that's still, there are people that have labs that are trying to do it, doing lab work combined with dynamical models. And the whole process is still not really clear. But anytime that they learn something, we feed it into our bigger models. And so what we've been doing is kind of high level, how do things form on a high level if you have different perturbers? I didn't talk about, we found lots of planets in binary star systems and in triple star systems. And so another thing we've been looking at is how planets form with these different stars perturbing the system. So with so many different knobs you can twist, it's impossible to get to that level. But if you're talking about what makes a planet, then yeah, so there's a lot of research on that, but it's not really what we consider when we're doing these sort of formation questions to answer these big level questions.
To what extent are these telescopes taking over the function of the proposed
I'm sorry, can you repeat the question?
To what extent are these telescopes taking over the function of the proposed terrestrial planet finder telescope project?
Oh, from the past?
Yeah.
Oh, okay. The question is, to what extent are these missions taking over the previously proposed terrestrial planet finder TPF mission? So, I mean, that's still a little bit before my age, and I'm kind of old. But I do remember that one of the first. So I work at NASA, and we hear a lot of funny terms and acronyms. But one of the first things I remember hearing about terrestrial planet finder was it wasn't canceled; it was indefinitely postponed. So that's pretty much all I remember from the terrestrial planet finder. I don't remember any specific details about what it was supposed to find or what parameter space it was supposed to probe. If you know that, then I can tell you.
Well, I think they're supposed to do direct imaging. I don't really know that much about that.
I mean, I probably knew because that's when I was just starting out. So, I mean, direct imaging, we have a lot of capabilities that I haven't talked about with just with James Webb. I haven't really talked about with WFIRST. I just kind of highlighted. There's a whole class of new flagship missions that are being proposed, like LUVOR and HABEX and OST, that have all different capabilities. And so I think it's a complicated question unless you actually told me what specific part. I think, yeah.
Are you finding the same with first generation stars in terms of the clumping and the planets around them? Or could it be like the energy be from like supernovas where the clumping happens where you maybe get the rounding or the planet formation?
Yeah, so again, that research of, I mean, so one thing, this is kind of tied loosely. So one of the smallest planets we found with Kepler is Kepler 37. And so this is a planet that was sub-Mercury, almost moon-sized. And at the time, we wanted to write a paper and say this is a new planet. But if you looked at the IAU definitions were strictly that it had rules about what is a planet. One was that it had to revolve around the sun, which that didn't tick off. But also it has to be spherical and it has to clear its orbit. So there are all these kind of definitions that people are trying to put for what makes a planet. But we also see lots of asteroids that are very, very non-spherical. We don't even have the resolution to see everything. I mean, we're sending OSIRIS-REx is sending a mission to these asteroids, and we're still learning about what they're made of. And so there's so much we don't know. And there's so much we don't know about what actually makes something spherical. We don't know the distribution of what is not spherical. And so these are all questions we're still probing. And as far as what makes something spherical, there isn't really a good rule of thumb, like it has to be a certain mass, because we'll see big things that are, spherical, and we'll see, there's basically every time we think we know something, we see something that doesn't agree. And so,
First generation stars, you see planets, you see
what do you mean first generation stars?
first stars in the universe. So, like supernovas, so that's when heavier elements were made. So I'm just wondering if the energy of the supernova, if that shot had some impact on planet formation.
Yeah, I don't think we can know that right now. But we are seeing lots of supernova from TESS, but that's irrelevant. Yeah, I don't think that's something we know, but apologies. Sure.
In the Kepler search for Earth-like planets around sun-like stars, we kind of know what the Goldilocks band is. Now, as we move into small, cooler stars, red dwarfs, with planets evolving very rapidly around the star, possibly bound like Mercury so they don't rotate.
Mhm.
What are the Goldilocks
So that is probably like the golden question, because I was a grad student at NASA Ames in, I guess, 1999, early 2000s. And at the time, I was very close to the SETI Institute. And so SETI is a search for extraterrestrial intelligence. And at that time, they were just having big workshops trying to understand the habitability of planets around M dwarfs. And this was before we even knew that planets orbited around them or they were prevalent. And at that time, Jill Tarter, who you might know, she was, I guess, if you see the movie Contact, that was kind of based on her character. But she was really interested in habitability of planets around M dwarfs. And at that time, she put out this thick paper basically going through all the challenges of habitability. And there's a lot. So as you mentioned, there's the tidal locking, because so one thing, if you have an Earth around the sun, you're far enough that you don't have to consider all of the star-planet connections. And then as you mentioned, if you have a planet around an M dwarf in the habitable zone, because they're smaller and cooler, then you're much closer in, and then you have to take into account a lot of things that we normally wouldn't think about with sun-like stars. And so one is flaring. Low-mass stars are really active, violently flaring stars. I have an intern here, Eileen, who is basically looking at hundreds and hundreds of tiny stars from M dwarfs. They're showing this huge diversity of different flarings all the time. So you get this UV radiation because it's close, like this, like the moon around the Earth. You get this tidal locking. So you get the one side facing the star at all times. There's a ton of things, like can you get photosynthesis if you're a planet around an M dwarf that only has infrared radiation and not solar radiation. So there's literally like 100 probably different problems trying to solve, can planets be habitable around these small stars. And this is one of the huge focuses of this SEEK collaboration, because we have basically scientists from almost every different regime trying to tackle these. We have scientists in the heliophysics division trying to see if you have energetic particles from small stars, if they would strip atmospheres. We're working on planet formation, flares, everything. And so it's a huge, big question. And as I mentioned, because these are the most prevalent stars, we know they often harbor Earth-sized planets. James Webb is going to be capable of really probing atmospheres of planets that orbit these M dwarfs. So really, M dwarfs have been the hot topic ever since, I would say, the last 10 years. And all of the questions like the one you asked are really hot topics of research. And you might see articles every day saying, oh no, it looks like M dwarf planets are off the table because someone found this. And then the next day, no, you'll see this. And so it's something that's one of the most exciting areas, I think, in exoplanet and planetary science. So I can't answer your question because it's one of the hardest questions to answer. But thanks for asking. Sorry, in the back. And then you'll get Yeah.
Principal reason why we get planet formation for things like Earth and Mars, but not in places like the asteroid belt?
That's another question. So when people have been studying the solar system and you look at all the observables, some of the puzzling things are, one is like, why is Mars small? Another is, why isn't there a planet in the asteroid belt? There's no reason. In fact, one of the first papers I ever did as a grad student was seeing if you could place a planet in the asteroid belt and seeing if it would be stable. And it turns out you can. You can put a terrestrial planet in the asteroid belt and it'll be stable. So there's no real reason it can't be. Why it's not there is another puzzle to our solar system. So it's a observation in our solar system. It's not really a constraint that we use because we're finding such a wide diversity of of other types of solar systems, if that makes sense. But it's a good question. People come up with like Planet V and Planet 5 and why. That's another active area. Like I love planet formation. I mean, I love doing observing and working on missions, but like ultimately planet formation is what I've been doing as a grad student in my independent research because of these questions. Like, why isn't there a planet there? Oh, yes, sorry.
It strikes me that exomoons would solve one of the problems of tidal locking in M-dwarf systems. The exomoon would get baked on every side as it circles its own planet. Will W first give us any exomoons?
So exomoons is also something that has been studied with Kepler. In our solar system, because where Earth is at, like you said, so we have the moon, Earth system, and the moon is tidally locked. I think you can, around M-dwarf systems, you can still have planets that are tidally locked without a moon. As far as detecting exomoons, people have been searching with Kepler and they found some hidden evidence, but it's really hard. It's really hard to find the small signal. And so what we've found, there have been a couple, probably you've heard some articles recently about, I think somebody found a Neptune-sized moon around a Jupiter-sized planet. So there have been some signals that look like moons, but the signals are so like it's really hard to find Earths and it's really hard to find Mercury's. Like we're really pushing the limits with Kepler. And finding moons, you're looking for like an extra little wiggle in that. And so to actually be confident is difficult. W first will find moon-sized planets, but not necessarily moons around other planets. Well, at least that's not its primary goal. Planet-sized moons. Yeah, but finding a satellite, I guess if I were to call it a satellite, is difficult. Finding a small planet, like Kepler 37 was a Mercury-sized planet. And that was pretty much how as far as we could push with Kepler. But we could find planets as small as Ceres with W first, but they might be, yeah.
Could
Yeah.
be the last question. You had one.
Given the kinds of telescopes that were available in 1755, what was thinking about that it's inferred he had a disk-based cosmology?
So I don't know what he was thinking about. That's I wasn't there. I guess there is some evidence that him and Laplace were some of the first to put forth some ideas that perhaps, looking at the observational evidence that they had at the time, that perhaps our planets formed. If you read enough about it, then people are, oh no, why did they think that? And there's all these problems. But it was kind of the first time they threw this idea out there. But I mean, ever since then, it's something, I guess that was kind of the first time, you could have enough evidence to kind of think about that.
My impression, I'm not a historian of science.
Yeah, I'm not a historian.
The stars and the planets were out there, and much as Ptolemy, they're there, and then, it's fixed.
Right.
The notion that there would be new ones emerging, or things could change, but it just seems like a very different mindset, even
Yeah.
conceive of it.
Yeah. No, it was, yeah, I'm not a historian, so I shouldn't even give my ideas, but yeah, you're right.
Well, thank you so much for talking about TESS, etc., and we'll expect more in the future.
Sure.
Thank you for coming.
Yeah, thank you for coming.